In this example, we're going to introduce you to the idea of the total differential of a mathematical function, and then we're going to use the idea of a total differential to try to interpret the coefficients in a regression model that might have natural logs on either the left side, the right side, or on both sides of the model. Okay? So the total differential idea in a single variable context would work like this. If we had a function y equals f of x, okay, which I know that all of you have seen at some point, we could write down an expression that said dy, or change in y. We can use these d's to denote changes, small changes. So the change in y could be written as df dx times dx, okay? Or if you wish, using alternative notation, f prime of x times dx, okay? And this is a definition, so there's not really anything we can argue about or debate. It's really just what is. What I like to do, however, is to see if we can't think about the story that this particular expression might be telling us. Well, if we think about what df dx is, or about what f prime is, we can think of that as a rate of change. So it's asking the question, how does f change when x goes up by a little bit, right? So as such, it's a rate of change. How does f change when x changes by a small amount? If we take that rate of change and we multiply it by some actual change in x, it should give us the total change in f, or in this case, the total change in y that would occur. Now let's try to generalize this to multiple variables. Okay, so let's suppose that we have y, and this y is a function of x1 and x2. Okay, so what would a total differential look like? All right. Well, in order to answer that, we need to introduce you to something that you intuitively know something about but might not know it by its formal name, and that is the partial derivative. So the partial derivative of f with respect to x1 is a slope of sorts. It's the change in f, or in this case the change in y, that occurs when x1 goes up by a small amount, holding x2 constant. So we treat x2 as a constant, and we look at what happens to f when x1 goes up by a little. So one way to think about this is to imagine that you have a three-dimensional surface, like a pile of dirt in the middle of the room, and if we point in the direction of one of the walls, that's the x1 direction. If we point in the direction of one of the other walls in the room, that's the other variable's direction. So change in f over the change in x is going to be the change in the height of the dirt pile when we take a step in the x1 direction, holding x2 constant. Okay, so we can think of these as derivatives with direction of sorts. So given that this is a partial derivative, and that this shows us how f changes when x1 changes, holding x2 constant, we might ask the question, well, what if x1 and x2 are both allowed to vary? How can we write down what the change in y would be in that case? So we can write, for example, dy, which is the total change in y that results from a change in x1 and x2 simultaneously, as the change in f with respect to x1 holding x2 constant times some actual change in x1 plus the change in f with respect to change in x2 times the actual change in x2. So what does this really mean? Well, this is the same kind of rate of change that we saw before. That's the rate of change of f with respect to x1. If we multiply that by some actual change in x1, we should get the total change in y due to a change in x1. We have two variables that can be varied simultaneously, so we have to add to that the change in f that would result when x2 changes by a little bit. And that gives us the total change in y. So this is a differential, a total differential right here, when we have a variable that has several variables in it. So we're going to see some of those as well. Okay, but that's the definition of a total differential applied to both single variate 1x 1y case and multivariate 2x's 1y case. Well, what does this have to do with logs? Okay, well, I kind of want to pick up on something that we saw in the other video, the other handout. Let's suppose that we had an econometric model that was expressed like this. Okay, I'm going to ignore the error term for simplicity now. We'll just suppose that we don't have to worry about that at the moment. We can add it later and treat it accordingly, but at the moment, let's suppose that we just have this function. You will run into econometric models where both the left-hand side has been logged and the right-hand side has been logged. And the question becomes, how do we interpret alpha 1 in this case? Well, one way to think about this is to simply imagine that this log of y is a variable, call it z, and this log of x is some other variable, call it w, and we're really just looking at z equals alpha 0 plus alpha 1 w. And we know how to interpret that, right? Alpha 1 is just dz over dw, right? But we know that z is the log of y, and we know that w is the log of x, so we can rewrite this as d log y over d log x, right? And then the question becomes, what is the meaning of d log y, and what is the meaning of d log x? Okay. Well, this d notation, d anything, is the total differential of that function, okay? So we can think of it that way. So we can think of d log y as well, let me put it this way. We can think of d log y as the derivative of log y times dy. So this can be rewritten as the derivative of log y with respect to y, okay, times dy. The derivative of log y from our log properties is 1 over y dy. Okay, so what we're saying in essence is that we have a function of y here, and we're trying to figure out what the total differential is, and we know that that's f prime of y times dy. Okay, that's a big prime, but that's that's what that's supposed to mean, f prime of y dy. So if this is the function of y that we're talking about here, 1 over y is its derivative, that's where I got this. I multiply by dy, that's the total differential of the numerator. I'm dividing it by d log x, so now I have a function of x. The total differential, d, times that function of, not times, but d of that function of x, the total differential of that function of x, is going to be 1 over x dx, because the derivative of log x with respect to x is 1 over x. Okay. Now look carefully at this expression, right? We have dy over y. That's like a change in y in the numerator divided by some initial y. Here we have dx, that's a change in x over x, right? What does that look like? If we had multiplied the numerator by 100 and the denominator by 100, we'd be looking at the percent change in y over the percent change in x, right? Well, if we multiply the top by 100 and the bottom by 100, the 100 over the 100 cancels. That is to say, it's equal to 1. It's like multiplying the whole thing by 1. So this, in fact, is equal to the percent change in y over the percent change in x. In other words, the interpretation of alpha 1 is the elasticity of y with respect to x. Okay? Elasticity is just the percent change in the left-hand side variable divided by the percent change in the right-hand side variable. Okay. We can extend this to multiple variables. Okay. So for example, we could sort of extend this argument and write log of y equals alpha 0 plus alpha 1 log of x1 plus alpha 2 log of x2. Okay? And the question would be, again, what is alpha 1? Well, we're going to argue that alpha 1 is the change in this variable. So it's change. We use the curly D's when we're talking about focusing on one variable at a time here. So the log of y over the change in the log of x1. And the implicit notation here indicates that we're treating x2 as a constant. Okay, so alpha 1 is the change in the log of y when the log of x1 goes up by a little bit, holding the log of x2 constant. All right? And this notation can still be interpreted as a differential. So we can treat this change in log y to mean the change in y over y. All right, we're going to interpret it as the change in y over y. And the denominator is going to be the change in x1 over x1. Again, if we had multiplied by 100 over 100, okay, this would have been the percent change in y over the percent change in x1. Well, this doesn't change the value of our expression, so even when those cancel, this is still the percent change in y over the percent change in x1, and as such, it's still an elasticity. Okay? What happens now if we log only one side of the regression and not the other? So I'm going to log the left side. Okay? And let's see if we can't interpret that. So now we have alpha 1 equals the change in the log of y over the change in x. Okay? d log y can be written out as before, dy over y dx. Okay? So how do we interpret that alpha 1 exactly? Well, this is very close to the percent change in y in the numerator from a 1 unit increase in x in the denominator. But in order to make it a percent change, we need to multiply the numerator by 100. That changes it from a fraction to a percentage. Okay? If we do that to the right-hand side of the equation, we have to do it to the left-hand side of the equation. So what we would say is that 100 times alpha 1 is equal to the percent change in y over the change in x. Or in other words, 100 times alpha 1 is the percent change in y from another unit of x. Okay? Okay, so if we had found that alpha 1, for example, was estimated to be 0.11 when our model was log y equals alpha 0 plus alpha 1x. Okay? How would we interpret that? Well, we know that 100 times 0.11 is the percent change in y when x increases by 1 unit. Okay? So we can take the 0.11, multiply by 100, that gives us 11. So this would tell us that y will go up by 11% on average when x1 goes up by 1 unit. Okay. To see what this would look like in practice, if you found out that alpha had what variable